Lesson 5, what we're going to do is kind of put to work this trigonometry that we've learned, just to try to apply that to real-world situations. And so what we're going to see is how we're going to use trigonometry to do indirect measurement. If we're trying to see how tall a building is, we don't use a tape measure, we use math. And so that is going to be our number one priority. There is a formula for finding the area of a triangle, and we've already explored this when we did our exploration into the law of cosines. When we drop that altitude from the right angle to the hypotenuse, we're able to find out what that height of that triangle is, and I alluded to that in our 8384 video. And so, so here, applying trigonometry to the real world, you'll see surveyors, etc., using tools that are measuring angles for elevation, angles of depression, to try to figure out how far away or how tall things might be. If we have known measurements in there, then we can use that information to do indirect measurements. And so if we're standing 100 feet away from the base of a building, and hopefully the building is straight up, so we are assuming that it's perpendicular to the ground, making right angle over here. And if we're using a measuring device that is 62 degrees, it's showing us that it's a 62-degree angle of elevation as we look up to the top of the building, then we can use trigonometry, specifically the tangent ratio, to find the height of the building. And so we would create an equation saying, oh, well, the tangent of 62 degrees is going to be, again, opposite over adjacent. And so we have the height in feet divided by 100 feet, taking the tangent of 62 degrees. When we cross multiply to solve, we'll have 100 times the tangent of 62 is equal to our height. And when we do that computation, which again you can do with your own calculators there, we're going to find that the answer is some number of feet will be the height of the building. So let your calculator do that work instead of me doing it for you. You know, your calculator can handle that. And so fill in that value to make sure that you are doing that correctly. All right, now I mentioned just a few moments ago, looking at an angle of elevation, you know, from one level up to another plane, if you want to say. All right, so we're measuring from one place looking up, but then there's also from this place maybe looking down. So if we're at an observation deck, you know, in New York City or something like that, I've got some pictures I'll show you. I went to see went up on top of the Empire State Building, not on the top of, but I went to the observation deck in the Empire State Building, and I could look down and I could see where the Statue of Liberty was, you know, out in the harbor there, and also, you know, could look down at other buildings and such. I was up at a certain level where I wasn't looking up to the tops of other buildings. I was far enough away from World Trade Center where I couldn't see to the top of that. I mean, I could see where it was, but it wasn't like I was looking up. It was just kind of felt like looking out. So the question is, what is that angle of elevation when we're looking up, or that angle of depression when we're looking down? All of these looking straight out are going to be parallel, you know, theoretically to each other. We know the Earth isn't flat, but at this scale, it appears to be so. But we can look down at an angle of depression or look up at an angle of elevation. If this individual is looking out, right, these are all parallel, they would be looking down at an angle of depression to see the person on the observation deck. All right, maybe they'd be looking up to see an airplane or a flock of birds or whatever else. If you're down on the ground and you're looking up at the observation deck, you're looking up at some angle of elevation. And so we're going to do a little bit of describing our situations as, hey, is this an angle of elevation that we are viewing from, or is it an angle of depression that we're viewing from? All right, so keeping that vocabulary straight is going to be helpful to us. So in this picture, go ahead and draw that diagram. And then, so describe each angle as it relates to the objects in the diagram. So the birds would look down at an angle of depression. If there's a person in the tree, all right, they're looking down at an angle of depression, or they're looking up at an angle of elevation at these birds. This individual is looking up at an angle of elevation. So angle 1 is an angle of elevation. Angle 2, you're looking down, is an angle of depression. Again, sorry for the handwriting. Hopefully you're listening to the words. Angle 3 is an angle of elevation. And then angle 4 is an angle of depression. Now that vocabulary is helpful to us as we are maybe reading a problem statement and having to draw a diagram to go along with it. If the diagram is already provided for us, we need to make sure that we're understanding where to put these angles. Now again, I've already said that these lines parallel to the horizon are, these horizontal lines, right, are going to be parallel to each other, which means that the angle at 1 is congruent to the angle at 2, that those are going to be alternate interior angles. And so my angle of elevation looking up to the top of the tree is going to be the same as the angle of depression looking down from the top of the tree. Likewise, this angle here is going to be congruent to that angle there. Those are alternate interior angles. Looking up to the birds is the same as looking down from the birds. But that might affect, again, how we draw our pictures and where we're drawing our segments, how we're labeling those segments, how we're measuring those segments, so that we can create drawings that are appropriate and then create our equations from those appropriate drawings. All right, so here, determine the distance from the bus to the base of the tower. So if this bus, from wherever it is looking up at an angle of elevation of 23 degrees, notice how I'm saying I'm looking up at an angle of elevation that's 23 degrees. If you're on top of the tower, you're looking down at the bus at a 23-degree angle of depression. All right? If you know that the tower you're looking down from is 180 feet tall, or if you're approaching from a bus, that you know that when you're looking up that tower is 180 feet tall, how far away is the bus from the tower? Well, that, being able to label that with what's our variable, what do we know, we can recognize that we have a 23-degree angle, a right angle, and we have a right triangle where I know that this is 180 feet, and this gives me a right triangle that looks like the right triangles we've been working with, right? We have an angle, we have a side, we don't know a side, all right? And we can use trigonometry to do that. You're gonna notice that we're gonna use a lot of tangent. It's not always tangent, but a lot of times it will be, because there are gonna be some tangible things that we measure. It's very rare that we have measured this distance for the hypotenuse, but maybe you're asking the question, if Spider-Man wants to get from the top of the building all the way down to the bus, what is the distance from Spider-Man to the bus? Not that he's gonna go in a straight line there, he's probably gonna swing, right, and go at a curve of some kind, but you get the idea. What is the actual distance there? Well, that's your hypotenuse. So how far away is the bus from the base of the tower? That is gonna be found by, again, doing opposite over adjacent. We will cross multiply to solve, and then we will divide to get x by itself. You can approximate that with your notes, again, in feet. Use your calculator to do that, and write that actual approximation in your calculator. We'll discuss that in class. All right. And so this is where it gets to the tough part, and this is being able to draw a diagram, example 2b. And so a park ranger sees a forest fire at a 35-degree angle of depression from his or her ranger station. The ranger's position is 100 feet off the ground. So they're standing in this tower, all right? They're standing in their tower, right? They've gone up the stairs, they're up here, and they are looking down at, again, parallel to the ground there, we've got our forest fire. Oh no, it's burning. All right, but they're looking down at an angle of depression that is 35 degrees. All right, we know that they are 100 feet off the ground. All right, the question is, how far is the ranger from the fire? That's x. How far is the ranger's station from the fire? All right, so the ranger can see where it is and know how far away it is. That's not actually, they're not going to be able to fly down there straight to it. They're going to have to go in a roundabout way down 100 feet of stairs and then, of course, over to the fire. So we want to know two things. How far is the ranger from the fire? That's where he or she are standing. And then, I guess it says he, but whatever. How far is the ranger's station from the fire? That's going to be y. And so we need to be able to draw the diagram so that we can do the right thing. This is going to be a situation where we know that this angle is going to be congruent to that angle. So it's also 35 degrees. So from this perspective, all right, or we can make this into a rectangle where this opposite side is also 100 feet. But the question is, from here to there, if they're looking at an angle of depression of 35, here's what is important. This angle right here is not 35 degrees. All right? The angle of depression, if we go back and check, the angle of depression is measured against the parallel. So the number one mistake that students make is that they put the 35 degrees here, when really the 35 degrees are kind of outside of this triangle, because it's off of that horizontal, and they're looking then down from that horizontal. That's their angle of depression. All right? Which means that this is not 35. In fact, this is 55 degrees. This is 35 degrees, all right? Because these together need to make a right angle. So this one is not 35, all right? But this one is 35. From this perspective, opposite over hypotenuse, we're going to use the sine of 35 is going to equal opposite over hypotenuse. We're going to get to cross multiply, and we're going to get to divide to know what x equals. That's what x equals. But if I want to find out exactly or approximate how many feet, we can use our calculator to do that division. So I have my calculator here, but I would love for you to use your calculator to type those in. We're very familiar with typing those in. That's going to be the you do part, is you write those values. How far is the ranger station? So how far is y here? Well, for this one, for y, we're going to use tangent. The tangent of 35 is equal to opposite over adjacent. When we cross multiply to solve, y times the tangent of 35 is equal to 100. We're going to divide by the tangent of 35 to find out what y equals. All right? To approximate that in feet, we're going to type that in our calculators. All right? So use your calculator to do that work, please. All right, drawing the diagram is hard. Labeling the correct angle of, is it elevation or depression? Not this angle here. Have we drawn the picture well to visualize what this story is telling us? All right, reading, if you know that reading is hard for you, understanding comprehension, reading comprehension, that kind of stuff, then obviously let's work with our neighbors, let's work with your teacher, communicate. If you need me to read any of these aloud to you, we can do that, but hopefully we can tag team that together to not feel like that's an overwhelming task. Again, on exam day, if that's an issue for you as well, then I don't want you to not understand how to draw the picture if you're having trouble reading the sentences. All right, that was part one. Part two should be quick and easy. Well, maybe not quick, but definitely it should be easy. That's the hope, that's the intent. We know that finding the area of a triangle is 1/2 base times height, or base times height divided by 2, if we're in how we learned that maybe in our middle grades or elementary grades. Here, this triangle, ABC, does not have an altitude drawn, and so we're going to have to draw that altitude. When we draw in that perpendicular to find out what our height is, we're going to recognize that the sine of this angle is going to be opposite over hypotenuse. It's going to be h over c, all right? Which means that the height can be found by multiplying both sides by c. C times the sine of this angle is going to give us the height of the triangle. Well, if we know that we take 1/2 times the base of the triangle times the height of the triangle, then the area of this triangle will be 1/2 times b times what h equals. And h equals c times the sine of a. So this is our formula for the area of a triangle. If we know the measure of this angle, we need to know this, and if we know the measure or the lengths of these two sides that include the angle. So if we have two sides in the included angle in a triangle, then in any triangle, it doesn't even have to be a right triangle, then we can find its area. All right, 1/2 b c sine a. And these are multiplied, right? That's a times. And so these are multiplied. So we're going to have this be our formula, that the area of the triangle is equal to 1/2 times b times c times the sine of a. Again, when we are labeling, when we are writing our formulas, we need to know what numbers go where. A formula is only as good as we are at putting the numbers into the right spots. All right? So we have to understand that this is the angle at point A, this is B, this is C. This is the angle at point A, here's B and C. It doesn't matter which one's B and C, right? It's basically 1/2 times the length of the sides times the sine of the angle. All right, now I know that this might be confusing because we have a capital A for area and a capital A for the angle that we're working with, and that obviously requires thinking when we have multiple letters referring to the same thing. So apologies that is maybe going to be an issue for us. But we're going to substitute in these values. And let our calculators do the work. When we do the work, we're going to get square meters, an approximation in square meters. Now, one of the things I did here is I said, oh, wait, I thought that B was 26, but here you wrote B was 12. The point there is it doesn't matter. All right, so if you're using your calculator and you're going to take 1 divided by 2 times 12 times 26 times the sine of 76, you are getting an approximation of how many square millimeters that is going to be. So let your calculator do that work. I will go over those answers in class when we go over this. But make sure that you upload that with your answers filled in after having used your calculator. All right, so this will tell us the area in square units. We want to make sure that we understand our square units for those triangles. If we know 2 side lengths and the included angle measure, and in any triangle, doesn't have to be a right triangle, we can find its area. That is it. That is all that we're dealing with in this lesson. There will be a part 1 work and a part 2 work. Those will be separate tasks that we'll do in class. Those should go pretty smoothly. I'm hoping, fingers crossed, that this part is pretty smooth and that this part will maybe be a little challenging, especially if we have to draw diagrams. Please let me know if you have questions.